So, how has graphene played a role in electronics packaging, and do you see it being used more often once it can be manufactured at an industrial scale?
So yes, graphene is one of the new materials. And you know how it's being publicized? If you read it out, it'll say graphene is the thinnest, it is the strongest, it's the most flexible material that's known. That's how people who sell graphene really sell it at that. And that is true. It's really true. Just to give you some numbers, it's 200 times more stronger than steel. It is 97% transparent. It's extremely light in weight, and it's flexible and stretchable. And all of this is true. But in terms for electronics, it's thermal conduct and it's electrical conductivity. Both of those are why it is such a fascinating material to work with. They say that graphene has got very high electrical conductivity because it is in zero overlap semi-metal. That's what it's a lingo, a technical term for why it has this super high conductivity to it. But again, if it's a monolayer event, it's a 2D graphene, you get all the ideal properties into it. But manufacturers are dealing with challenges where they get these multiple layers. They've got so many layers and they're all entangled. They're not really we need this one layer stacked neatly over the other for it to give the final properties. And that's not happening. That's where manufacturers are getting into two-dimensional processes. They say that, there are certain nano CVD-like processes where 90% of graphene can be a single layer. And they say if we are able to manufacture in large quantities, it will be 1 million times faster than graphene, which is deposited by CVD. It is also 100 times faster in terms of conductivity, the graphite, which is used in batteries. So again, because it has such beautiful thermal conductivity, it can be used. One additional thing why it is picking up that much interest is because it has good compatibility with silicon. The CTE, or coefficient of thermal expansion, of graphene and copper are very similar. And so for packaging application, where you need zero stress between an interconnection, so if you have graphene-like material, that can act as another substrate on the other end, the CTE mismatch is less, and it's called as a zero stress packaging. And that can be used as a heat spreaders and packaging. So it has a lot of application. Also, flexible and wearable electronics. They can take big advantage of graphene because, again, it has beautiful mechanical properties and it has high electrical conductivity. Right now, these touch screens, what is the material that's made of? So ITOs, okay? This is indium tin oxide. So ITO does its job beautifully. The only problem is it's very brittle. So if you have graphene-based electronics, which are flexible, and they have these 97% clear. So it won't have that turbidity. It can be used. So all these shatter-proof glass and all, it's still glass, not graphene yet, but graphene has potential application in those areas too. So it's combining its thermal properties, electrical properties, optical properties. So graphene is the new CNT, carbon nanotubes, that we're talking about.
That's
Again,
awesome.
I think the limitation would be it needs to talk to other thing, and the interface should be fairly compatible.
And so one quick term there, you said it's a zero overlap semi-metal. So Could you just define that term a little bit and unpack exactly what that means?
So semi-metals are basically materials that have properties in between metals, non-metals, and semiconductors. So we know there are three classes of materials, right? There is metals, there are insulators or dielectrics, and then there are semiconductors. And then there are a few materials that are semi-metal in nature because their properties are between the semiconductor and metal because they're very beautiful electronic configuration. They have this partially filled orbital that the electrons can jump and hop around in a way that it can very easily be tuned into either semiconductor or fuel. And graphene has those properties because of its very tight structure. The carbon-carbon bond between graphene is much tighter than any other carbon product out there. And because it is such strongly held together, very covalent bonds, even thermal vibrations won't jiggle or won't perturb the bond between those carbon atoms within graphene. And therefore, it has very beautiful thermal properties. It's used as thermal interface materials, or TIM as they call them, because of this semi-metal behavior.
And so is that zero overlap parts that come from its electronic configuration? Or
yes,
is that...
It is from the electronic configuration. The 3p and the 3d orbitals, they kind of have a configuration in a way that the electrons can easily move between these energy levels.
Hello, everyone. Just a quick definition before we get into this next section of the episode.
So this definition is to define 3.5 and 2.6 semiconductors. So what exactly are they? Well, 3.5 and 2.6 semiconductors are a way of broadly referring to and classifying two major categories of compound semiconductors. The designation 3.5 or 2.6 refers to which group in the periodic table the elements in the compound semiconductor are from. For example, a commonly studied 3.5 semiconductor material is gallium nitride, or sometimes called GaN for short because of the atomic symbols, where gallium is from the third group of the periodic table, and nitrogen, which in its ionic form is called nitride, is from the fifth group in the periodic table. Compound semiconductors contain two or more elements to form the semiconductor material, such as gallium nitride, whereas silicon only contains one element. We'll be talking a little bit more about the advantages and disadvantages of these materials in the next section of this episode. So we hope you enjoy. So silicon is obviously the big name material in this space for the most part, but there are certain parts of this industry which are reaching some limits with conventional silicon-based semiconductors. So perhaps this is more in the space of 3.5 or 2.6 semiconductors would be in making this next generation of materials that will make a significant impact on the electronics field.
So let's talk about why silicon, because again, it has dominated your electronic industry forever. And it's coming because A, it's very cheap and it can have a perfect crystal structure. You can dope it, make it as conducting as you want. You can make it as insulating as you want. It has a good combination of, charge carriers, which means the electrons and the holes and velocity. So you can do a lot with silicon. And it's coming to a limit. And that's why 3.5 semiconductors we talked about are coming up. Gallium nitride has been a very nice alternative, and especially for power electronics. Why? Because gallium nitride, A, it performs better as compared to silicon at higher voltages, at higher temperatures. It has much faster frequency speeds, switches faster. So all of these things that I talked about, which is, temperature, voltage, and frequency, what do they all drive into? Finally, your systems to be more compact, faster, have lower switch losses, higher frequency, efficiency. All of these are better. So gallium nitride or 3.5 semiconductors for that matter is gaining interest. Obviously, they have some challenges like everything else. There are three that I can mention. The first one is 3.5 semiconductors are more difficult to handle than silicon. They're not as commonly available. And then they are also much smaller in size. They're like these massive 20-inch silicon wafers that you can work and make billions of transistors on. Here with gallium nitride, they're much more costlier and they're much smaller in size. Also, some of the other like gallium arsenide, just the cost of processing it, the facilities that I have, processing facility, they say will cost about 20 times more than on a silicon wafer, just to start with. So now you have to marry some of the problems of these new 3.5 semiconductors and some of the possibility of silicon together. And for that, there's a new material called as scandium aluminum nitride. And so it's combining both materials, your gallium nitride and your scandium aluminum nitride. And people, when they combine these two, they are lowering the energy demand that goes into making those. And they can work with larger pieces and use all the advantage that gallium nitride have, frequency switches and speeds and high voltage performance. All of these advancements are good and happening, but like I said, they are not the bottleneck for our next electronics. You may kill the research of making another of these fancy semiconductor devices because they're not bringing manifold advantages into it. Of course, the cost is a major problem. So other than the cost, performance-wise, we're not adding much value to it.
Okay.
So what drives, again, those advancements, those heterogeneous integration, that's where the new next generation changes in electronics would be.